Welcome back to our YouTube channel, all about science, space, and technology. This is going to blow your mind. Imagine holding the power to see things thousands of times smaller than the width of a human hair. Think about exploring the intricate details of a butterfly's wing, revealing a mosaic of colors and textures beyond our normal perception. This is the power of the electron microscope, an instrument that has revolutionized our understanding of the microscopic world. Since their invention in the 1930s, electron microscopes have become indispensable tools in various scientific fields. They have allowed us to peer into the very building blocks of life, revealing the complex machinery within our cells. They have unveiled the secrets of materials at the atomic level, paving the way for advancements in technology and engineering. The journey into the heart of matter begins with understanding the limitations of traditional light microscopes. These instruments, while valuable for observing larger structures, rely on visible light to illuminate specimens. However, the wavelength of visible light limits their resolving power, making it impossible to discern objects smaller than a few hundred nanometers. This is where electron microscopes step in, offering a window into a realm far beyond the reach of light. By harnessing the unique properties of electrons, these remarkable instruments have unlocked a universe of knowledge hidden within the microcosm. To comprehend the power of electron microscopes, we must first understand the concept of resolution. In microscopy, resolution refers to the ability to distinguish between two closely spaced objects. The smaller the details an instrument can resolve, the higher its resolution. Light microscopes, limited by the wavelength of visible light, struggle to resolve objects smaller than 200 nanometers. This limitation arises from the wave nature of light, which causes it to diffract or bend around small objects, blurring the image. Electron microscopes overcome this limitation by utilizing a beam of electrons instead of light. Electrons, despite their particle-like behavior, also exhibit wave-like properties, but with a much shorter wavelength than visible light. This shorter wavelength allows electron microscopes to achieve resolutions down to a fraction of a nanometer, revealing a world of detail previously invisible to us. This remarkable leap in resolution is akin to discovering a new continent on Earth. It has opened our eyes to the intricate structures and processes that govern the natural world at the nanoscale. From the delicate arrangement of atoms in a crystal to the complex machinery within a single cell, electron microscopes have unveiled a universe of wonder hidden within the ordinary. The heart of an electron microscope lies in its ability to manipulate and focus a beam of electrons. This beam, generated by an electron gun, is accelerated by a high voltage and then passed through a series of electromagnetic lenses. These lenses, analogous to the glass lenses in a light microscope, act as focusing elements, but instead of bending light, they control the path of electrons using magnetic fields. By carefully adjusting the strength and shape of these fields, scientists can focus the electron beam onto a tiny spot on the specimen. As the electron beam interacts with the specimen, several phenomena occur. Some electrons pass straight through, while others are scattered or absorbed, depending on the density and composition of the material. These interactions are captured by detectors, which convert the electron signals into images or spectra. Two main types of electron microscopes exist: transmission electron microscopes, or TEMs, and scanning electron microscopes, or SEMs. TEMs, like powerful X-ray machines, transmit the electron beam through an ultra-thin section of the specimen, creating highly magnified images of its internal structure. SEMs, on the other hand, scan the electron beam across the surface of the specimen, producing detailed three-dimensional images of its topography. The invention of the electron microscope marked a turning point in scientific history. It opened up a new realm of exploration, allowing us to see and understand the world in ways never before imagined. From the smallest viruses to the most complex materials, electron microscopes have become essential tools in a vast array of scientific disciplines. This knowledge has been instrumental in developing new drugs, vaccines, and diagnostic tools. Materials scientists rely on electron microscopes to study the structure and properties of materials at the atomic level. Despite challenges, the electron microscope remains an indispensable tool for scientific discovery, pushing the boundaries of our knowledge.